Hello, ladies and gentlemen. Welcome to module number 6. 6 in a series of 9 modules for the course. Hopefully by now you will have completed your midterm exam or on the way to completing it. We'll do a walkthrough of the midterm exam as soon as everybody's done with it and I get it and grade it. And then everybody can see how you did. So for now, let's go ahead and go through module number 6. So the main ideas here is that linear regression provides methods for examining the association between a quantitative response variable and a set of possible predictor variables. Usually we draw it like this, right? The predictor over here on the x-axis and the outcome variable outcome, there we go, on the y-axis. And if there's a relationship, then if I give you a number for the predictor, you should be able to give me the probability of an outcome or the outcome that is most probable, and you draw a line, and then that's where the two lines meet. It should only be used with data that exhibit linear or approximately linear relationships. Okay, something that we'd like to say is the acronym LEIN. Linear independent observations that are normally distributed and with equal variances. So we'll go through all of that. Simple linear regression is used to estimate the linear relationships between a response variable y and a single predictor x. The response variable y can be referred to as a dependent variable, and the predictor is the independent variable. So y is dependent on x, and x is independent of anything. And this is a statistical model, okay? So y is the outcome, x is a predictor, b is the intercept. So when x is 0, so on this line here, when x is 0 right here, and then what is y? It should be the intercept, and that is also equal to b subset 0. Okay, because if you plug in a 0 right there for the x, then this whole thing cancels out, and all you're left is y equals bo. There you go. Multiple linear regression is used to estimate the linear relationship between a response variable and several predictors. It's a little bit more complicated, right? It's hard to do on a two-dimensional image like this, right? Because you have an x here, and that's x1, and then you have, if you have y, excuse me. But how do you do the x2, right? Where do you do it? It's a little more complicated, right? And so we can say that one line is x2 is equal to if x2 is equal to 1, and another one is if x2 is equal to 2, and then another line if x2 is equal to 3. And so then yes, you would be able to tell me that if x1 is equal to this and if x2 is equal to 1, then my y should be over here somewhere. Or if x1 is equal to this and x2 is equal to 2, then my y should be over here somewhere. And so on and so forth. So let's look at scatter plots, which tell us if a relationship is a little bit linear. So you see here from the Prevent study, the number of participants, the cognitive function, score range, right? Random sample of 500 participants. And here's your scatter plot. Is there a linear relationship here? So for every increase in years, is there some sort of a pattern to the y's? I think so, and I think it goes a little bit like this, right? So if I told you somebody who's 70 years old, their average score would be somewhere around right there. Further, if you want to just look at this a little bit more critically, let's say 70 is this line right here. These are all those people on that line are people who are 70 years old, and you can see the average is probably somewhere around there, right? And then this number is a little bit normally distributed like that based on the numbers right there. Excuse me. So this is something that you just kind of eyeball here just to kind of understand, but then R will do the rest of the work for you. So it does appear to be linear, and Lab 1 showed you fitting and interpreting a line as well as evaluating whether the assumptions for linear regression are satisfied. Again, the assumptions are LEIN, linear, independent, normally distributed equal variances. There are 4 assumptions. Here we go. LEIN, linearity, constant variability, which is the E in LEIN, so that's the L. Independent observations is the I, and normality of the residuals. So we'll talk about that later. Least squares regression. Okay, so when we're doing the linear regression, as I said, if I give you a value of x here, and we know that the linear association goes kind of like this, but we have all these points along the way, right? We know that this is a line, and the residual is the distance between a point on the scatter plot and the predicted value on the regression line. So the distance between here and here is one residual, here and here is another, here and here is another one right there, another one right there, another one right there. So these are the residuals, and we expect this distance or this distance residual to be normally distributed. So again, you see them here. So these are the residuals. Again, it's just like what I drew out for you guys. Estimating a line using least squares. The least squares regression line is a line which minimizes the sum of the squared residuals for all the points on the plot. In other words, the least square line is a line with coefficients b0 and b1 such as the quantity is like this is the smallest, where n is the number of data points. Okay, so again, what we're doing is that if we have a whole bunch of numbers, a whole bunch of dots, which are numbers, we want to draw the line in a way that the distance between those dots, those numbers, and that line is the least. The distance squared, because you're going to have some negative distances, right? Positive over here, negative over here. You want to square that to get rid of the negative sign. But it's the least. The general for a general population of ordered pairs, the population regression model is this, where the residuals are normally distributed, or the error term, which is the population parameter for the residuals. Since the mean of the error term is 0, the population model can also be written as this. Okay? Where the expected value of y based on the predictor of x. So remember, this is the expected value of y. It's not the actual value of y. It's what you expect on the average and in the long run. The coefficients of the line in the least square regressions. So these are if these look familiar to you, they should. Right? Beta 0, beta 1 are parameters with estimates beta or b0 and b1. These estimates can be calculated from summary statistics. So here we have the sample mean of y, the sample mean of x, the standard deviations of x and y, the correlation, which will equal to b1, and then you plug in b1 over here, and you already have the rest, so you will be able to get b0. Now remember, what is b0? Is the value of y when x equals to 0. So R can do this for you very simply. LM, and then the samples that you want to regress, right? It gives you the intercept when x is equal to 0, when age is equal to 0. So this is your x. This is your y. When this is 0, then the intercept will be 137. And then this is your coefficient for x. This is what you would put. So in the formula, your expected value of RFFT is the intercept minus, because it's a negative number there, 1.26 times x. Okay? And then you can check your assumptions. Always check your assumptions. The assumptions in linear regression are linearity, constant variability, independent observations, and approximate normality of the residuals. Independence has to be checked by considering the study design. You make sure that each observation is independent of other observations. And then you look at the residual plots, okay, and the normal probability plots. So here you have your residuals, right? And if they all fall along the line, and their distance is pretty much the same, that's pretty good. And then just think of this, looking at the residuals, so the distance between the points here. And you want this to be nice and straight like this, that it doesn't look like a cone or some other weird, as long as it's nice and straight. you have constant variability. So the variance between this point here is the same as the variance over here, is the same as the variance. It's not going to be exactly the same, but pretty constant. Now look at this. Here we have a weird thing, even though this looks pretty straight, right? But the problem is that it isn't straight. If you kind of look at it, it kind of goes like that, right? And so then that's where we have it over here. So checking the normality of the residuals, it is fundamental. You need to have that. If you don't have that, your linear regression is not valid, basically. Okay. The error term is assumed to be normally distributed with mean 0 and standard deviation sigma. Normality of the residuals is checked using normal probability plots. The plots were used to check the normality assumption in ANOVA, and it's discussed in section 337. So let's interpret a linear model. Here we're going to have a categorical predictor with 2 levels. Okay. Although the response variable in linear regression is necessarily numerical, the predictor can be either numerical or categorical. Okay. So again, I apologize that this got cut off, but here we're looking at the change in arm strength by sex from the famous study. And then we calculate the mean in each group. And so here's the mean in females, and here's the mean in males. Fit it to a linear model. Look at that. The intercept here. The intercept here is just like that. And if it's male, then it's 62.93 minus 23.59, which is, could it be 39.23? Okay, so this is kind of telling you 2 things, right? The mean in each group, and then you can fit it in the line. The intercept is the mean of one category, the baseline category. So the baseline is females. So here females are coded as 0. So x is equal to 0, or x1. And then x1 is equal to 1 if it's males. Right, and that's why you put a 1 there, and it's 23.59. This is 39.34, by the way. Not quite 39.23, but pretty close. So R squared to describe the strength of a fit, the quantity of R squared, right? The correlation coefficient R measures the strength of the linear relationship between the 2 variables. It is more common to use R squared to measure the strength of a linear fit. R squared is the amount of variation in the response explained by the least square lines. Okay, so one question that I might ask you is, what percentage of the variation in the linear regression, or the variation in Y, is explained by an R squared of 0.79? And the answer is 79%. Okay, and there's different formulas. You know, don't get too hung up on the formulas. Just know that there's formulas to calculate it. The variability of the unexplained by the model is the unexplained. So explained minus unexplained over total explained gives you a percentage. In Lab 4, you should have looked at that. So this is from a comic, and so I don't trust linear regressions when it's harder to guess the direction of the correlation from the scatter plot than to find new constellations on it. Only 6% of the variation in these dots is explained by that line. No, not very strong. It's almost a straight line. So what about outliers? So depending on the position, data points on a scatter plot have varying degrees of contribution to the estimated coefficients of a regression line. So if you have a line that has a lot of outliers, but then everything else is over here, it's going to influence your ultimate line, right? Your line should be somewhere around here, but these outliers over here are going to shift it ever so slightly upwards, maybe even bend it a little bit. So a data point is considered a regression outlier if its value from the responsive variable does not follow the general linear trend in the data. So these ones up here. If an observation has a strong effect on the estimated coefficients, such that the estimates change substantially when the observation is omitted, then it's considered influential. Outliers with high leverage may be influential, and advanced courses in regression have formal definitions for these terms, so don't worry too much about it. It's just important to simply be able to identify influential points. So here's a slide that will show a scatter plot of infant mortality versus number of doctors. Okay, look at this outlier. What is it doing? Right, generally you should have a line here, but that outlier shifted our relationship, an entire relationship. Do you think it's influential? I bet it is. Okay, so to identify the influential point, it corresponds to the District of Columbia, where there are approximately 800 doctors per 100,000 members of the population, but the mortality rate is still really high. This observation has high leverage, since 800 is a high value for the predictor value. The observation is an outlier, since it's an unusually high y value paired with a high x value. It's influential because its inclusion substantially affects the estimated coefficients, reversing the sign of the slope. It went from a negative to a positive. All right. And statistical inference. So we go back to our line. Hint. Remember this line. I know what goes into this line. The slope and the intercept of the regression line are estimates of the population parameters. Okay. So a null hypothesis is that beta 1 is equal to 0, and the two are not associated. So in this case, the line is completely flat. The slope of the line is 0. Okay. The alternative is it's not flat. It's either this or this. Okay. The t-statistic has degrees of freedom n minus 2, where n is the number of ordered pairs in the data set. And this is how you calculate the t-statistic. Standard error of beta of b1. b1 over the standard error of b1. And the value of b1, 0 equals 0 when the null hypothesis is one of no association. 95% confidence interval looks pretty familiar, right? The point on the t-distribution with n minus 2 degrees of freedom and alpha divided by 2 area to the right. 0.05 usually. Alpha divided by 2 is 0.025. Again, 0.025. 0.02025 is the area under the curve. This is your t. All right. Formulas for calculating the standard errors of the model coefficients are in section 6.4. In practice, statistical software with R is used to obtain t-statistics and p-values for linear models. So remember I told you, R uses t because remember, when n is greater than 30, t is approximately the same as z. So you might as well just use t because sometimes you might have a low end. All right. And that's it. That's it for section number 6. If you have any questions, comments, or concerns, let me know in the discussion forum. Send me an email. I hope you all finish the midterm okay. And, we're almost there, guys. We just have section 7, 8, and 9. Remember, number 9 will not have a quiz. Number 9 is just an extra on logistic regression. Just a couple more sections, and then we'll be done. And hopefully you'll get to have a good summer, get vaccinated, and everything starts to go back to normal. Let's hope so. Thank you.